Thank you all for having me. My name is Mark Clifton, and I'm the Executive Director of the Northshore Mosquito Abatement District. Just north of the city of Chicago, there's an aerial shot looking south across our district towards Chicago. And today I'm going to talk about another kind of interesting aspect to resistance that I think sometimes is overlooked, as well as its implications for viral transmission and ULV control. And that is really that blood-fed mosquitoes exhibit a kind of transient tolerance to pyrethroid materials. So let me get started here. So there's studies that have looked at the impact of natural kind of existing populations are rare. There's really not a ton of them. There's a lot of studies that look at the effect of an insecticide on an insect in a laboratory. There's a variety of studies that look at cage field trials, especially in our field. But when you start getting out towards an impact of ULV or a treatment on a whole natural existing population, or even the impact on disease or disease transmission, those studies are much more difficult, and so they're much rarer. And so this whole line of research really started because we wanted to understand what our ground-based ULV approach was doing to a natural population. We've all seen cage field trials. We know how things work in the lab, but we wanted to know, how is this going to work out in the real world, in the wild? And the first question that we really had to ask ourselves is, what makes up a population of mosquitoes? Well, in our district, we're about 70 square miles, so rather compact. We have 13 different communities, and you could think of a population maybe as all the mosquitoes that exist within our district. That could be our population. We could divide this population further because we do have two main vector species for West Nile virus. That's Culex restruens and Culex pipiens. So that maybe could be our population. But you could also divide your population even finer. Your entire Culex population is actually a mixture of mosquitoes of all different ages and all different physiological statuses. There are blood-fed Culex, ones that have just fed on blood either 24 or 48 hours ago. You have gravid Culex who are looking for a place to maybe deposit eggs. They've digested their blood meal. You have host seeking, either they're newly emerged or they've laid eggs and they're looking for their host. There's also male mosquitoes and possibly other kinds of physiological state of mosquitoes out there. And there's a variety of different trapping mechanisms for each of these subtypes or subpopulations of mosquitoes: resting traps, gravid baited traps like we use here, CDC gravid traps, or maybe host baited traps with CO2. And so for us to observe a natural population during and after a ULV treatment, we decided to set up stations that contained a modified gravid trap that contains a BG counter, and then the standard BG Sentinel with a BG counter. And the idea here was to collect really fine resolution data before, during, and after a ULV treatment. And if you're not familiar with the BG counter, it essentially can count mosquitoes and relay that data wirelessly every 15 minutes. So it provides a really sensitive view on what's happening with the ULV treatment. So we did a series of treatments in 2018 in Skokie, Illinois, which is a kind of a dense suburban urban area in our treatment maps C11 and C18. We did a variety of treatments throughout July during the height of our viral prevalence and kind of West Nile transmission season, the end of July and to August. And we use Duet, which is a synergized pyrethroid, at about the maximum label rate, just under the maximum, by truck with a Clark ULV Clark Cougar. And then we monitor our BG counters continuously during that time to see what was going on. And so as you would expect, you do see a reduction when we apply the material by ground-based ULV. In dark gray is our host-seeking mosquitoes, and they were reduced. And then a few days later, you'd see a rebound after that reduction. But what was interesting is with gravid mosquitoes, we didn't really see the same reduction. In one case, there was a reduction. In another case, the population kind of went up. And in another case, the population just kind of moved sideways. So we started seeing that our host seeking and our gravid mosquitoes were behaving differently to this ULV treatment. We expected them to be identical, and that really wasn't the case. In C11, we didn't look at gravids, but just host-seeking mosquitoes. And again, we saw a pretty clear indication that that ULV reduces the population when it's done, and then followed by a rebound sometime thereafter. Just to visualize the difference in effect between gravid mosquitoes and host-seeking, we used a bivariate analysis, and we put host-seeking female mosquitoes on the x-axis and gravid mosquitoes on the y-axis. And then we connected with arrows the day before to the day after treatment. And so this way you can visualize the effect of treatment on both populations. The fact that the arrows move strongly to the left indicates host-seeking mosquitoes were being controlled, but the fact that the arrows don't move strongly down indicates that gravid mosquitoes were not really being controlled the same way. We really would have expected a similar result. And in one case, the population of gravid mosquitoes actually went up over after treatment. So really inconsistent results. To put numbers to this, we basically over 5 treatments found about a 65% reduction before when you compare after treatment to before. And this was really pretty regular. There was 63, 69, 63, 68. So really about 65% pretty consistently. If you look at gravid mosquitoes below that, you see that they're only controlled about 30% mortality, or a change of 30%. And that was really irregular, everywhere from minus 68% to increases of 23%. You see in host-seeking mosquitoes, we had some large rebounds in population after the treatment, and then host-seeking mosquitoes, you just didn't see that same pattern. So these two kind of subpopulations were definitely behaving differently. What was most concerning is we really expected better control at that label rate in our host, at least our host-seeking mosquitoes. We expected, something upwards of 90%, we were hoping, and we only saw a really transient 65%. So this really got us curious about what was going on. And we had no information about resistance in this district that had ever been produced prior to this. So we went back to the basics with the CDC bottle bioassay. Probably should have done this first before trialing, spending all summer doing field trials, but sometimes you just take the route as it unfolds. We've done hundreds of bottles in the last 4 years looking at sumithrin, permethrin, and malathion, and we see averaged across the whole district only about a 74% of mortality with sumithrin and about 59% with permethrin. And then parallel work by Chris Stone at the Illinois Natural History Survey Medical Entomology Laboratory has found this as a common pattern throughout the state of Illinois. Permethrin and malathion resistance can be found just about everywhere. We also went back to the cage field trial to try to understand what a susceptible versus our Northshore resistant mosquito would look like. And so we ran a trial side by side. And again, you see, when we use Duet at that kind of upper label, against susceptible mosquitoes, we got fairly, acceptable control. And then against our Northshore wild type resistant mosquitoes, again, 53%. So all the lines of evidence are kind of converging to the same general trend. You have 74% mortality in the bottle bioassay, at 53% in a cage field trial, and 65% mortality in a natural population. So there's a substantial level of resistance that exists in our Culex pipiens populations. Our Culex restruans seem completely susceptible to all of these same materials. When I don't have the data here, but they don't show the same pattern whatsoever. Now, going back to the gravid mosquitoes, this was the next part of the puzzle that we really wanted to understand. Why are these only half as well controlled as their host-seeking counterparts? And half the time, the answers can be found deep in the literature. So going back to 1987, we find that this has been addressed in the literature in the past, and it has implications for what is happening today. 1987, fenvalerate and permethrin, the LD50 had to be, took basically twice the amount of material to kill Culex pipiens 24 hours after a blood meal. The LD50 was nearly double for both of those non-synergized single AI materials. And if you look at in 1990, a similar trend was found with Culex pipiens and synergized resmethrin, where it basically double the amount of material was required at 48 hours after a blood meal. So what we're looking at here is you need basically twice the amount of material to kill mosquitoes, or Culex mosquitoes at least, somewhere 24 to 48 hours after a blood meal. Banu did some work with the valence formulation as well as with Duet and a wind tunnel to kind of re-explore these prior results, and found that with susceptible mosquitoes, we didn't see, or he didn't see in the wind tunnel experiments very much of a change after blood feeding. But when you use resistant mosquitoes, you again see the same pattern at 48 hours after a blood meal. You have 65% mortality in non-blood fed, and then you have, that's right over here, and then you have 35% mortality in blood fed. Again, about half of the mortality once they're blood fed. It's interesting, the valent product work or formulation worked really well, even with blood fed mosquitoes. Even if they're resistant, you remained upwards of 90% mortality. So that's really promising. So just to summarize some of the results we've been seeing, we have gravid mosquitoes exhibit about half mortality when they're resistant as compared to host-seeking mosquitoes. So in the wind tunnel experiment, we had 66% mortality and then down to 35% after a blood meal. Okay, so what does this all mean? Well, it means that mosquitoes are not all just one big fungible population. Every day, a new cohort of mosquitoes is emerging, and each cohort is different than the cohort that came the day before. An individual mosquito, and this is simulated data to show the pattern, but an individual mosquito is really cycling through various levels of susceptibility. They spend about half of their life with far reduced susceptibility because they've blood fed, and about half their life they're host seeking and they're more susceptible. And then you add in all the other kinds of tolerances that we learned about today, metabolic and KDR, and their total mortality just really drops, or the mortality that's available really drops. And so there's a way of trying to understand what's going on if you want to apply a ULV treatment to a population. And this is a model that was adapted from Chester Moore's work in 1990 that I updated for Excel to try and understand what does it mean when you look at 100 mosquitoes and they're all of different ages and they're all of different physiological statuses and they're all of different resistance statuses. What's going to happen with that treatment? And so in this model, which I think is a great conceptual exercise, and remember, this is all simulated data, but it helps us keep track of what's going on with this highly complex, highly structured population. We have a random number of mosquitoes that are entering the model I put it between 75 and 125 enter the model every day. The model progresses from left to right. So days in the model go 1, 2, 3, 4 as the model progresses. And the age of the mosquito that enter the model progress as you move down. So this way you're matching, you have a kind of an encyclopedia, say on day 10, of all the mosquitoes that exist and all of their different ages and gonotrophic states. Mosquitoes move diagonally through the model, and they suffer like a 5% daily mortality. So they have a 95% daily survival probability every day. So there's a natural attrition that occurs to the population as they move down these steps in the model. So if you have 119 enter on day 1, you'll have 113 and 102 and so on and so forth. And then by the time you get out to like the third gonotrophic cycle, there's not that many mosquitoes, but those are the most important mosquitoes because they're the ones most likely to have a disseminated infection. Those are the ones that are going to infect humans or infect birds. And so those are really the key if you're looking at a public health intervention, is those older mosquitoes. So we can assess the effect of a ULV treatment by just assigning a mortality to each of these different life stages or gonotrophic stages. So imagine we have a material that has a 95% mortality for all stages. And there are materials that are probably pretty close to this that are non-discriminating when it comes to gonotrophic state. And what you see is a really broad effect on the age structure of the population. You don't see any older mosquitoes, and they don't exist for around 10 days. All different gonotrophic states are well controlled. Blood fed 24 hours, blood fed 48 hours. They're all just kind of wiped out. You see the biggest reductions in your population, of course, in your newly emerged, because they're the most abundant part of your population. I want to contrast this with the kind of treatment effect that we're seeing here in the North Shore. We have in host-seeking mosquitoes about a 65% mortality. If they're blood fed 24 hours, I picked the midway. This is a conceptual exercise, about 47%. Blood fed 48 hours, about a 29% mortality. And then their susceptibility returns at 72 hours after blood feeding. And what you see here is broad swaths of the population are able to persist, especially in your blood fed 24 hours and 48 hours in their first gonotrophic cycle. They kind of produce a wave that persists out into that older mosquito cohort, days 23 or 24 in the model, 2-week-old mosquitoes. You see that there, and you see it in mosquitoes in their third gonotrophic cycle as well. And then all your other mosquitoes are just poorly controlled. So if you're looking at your oldest mosquitoes, they're still there. The effect on the age structure was not nearly so profound. So I just want to highlight again what these two different scenarios look like. The top is 95% control through all life stages, and the bottom is a variable control coupled with some level of resistance. And you can see, and if you look at your potentially infected mosquitoes, and this is in the red squares, potentially infected mosquitoes are any mosquito from basically day 3 on. They've blood fed and they're potentially infected. And you see when you have 95% control, you get a tremendous reduction down to just 18 mosquitoes, and then a slow buildup back to the model's steady state. If you're dealing with resistance, they're barely impacted. You still see 2/3 of the mosquitoes still exist that are potentially infected with West Nile. We can look at this a little finer, maybe more graphically. This is the same data, but just displayed on a typical line graph. And your susceptible mosquitoes, again, are well controlled if your treatment is on day 14, and then you see a rebuilding of the population. Resistant mosquitoes seem to be not so poorly controlled. It seems like it's almost as good. The problem here is that difference between susceptible and resistance is almost completely made up of newly emerged uninfected mosquitoes, not the part of the population that's the most important if you're looking at a public health intervention. We can look at this another way by only identifying those mosquitoes that are older than 11 days. And remember, these are the mosquitoes that have a disseminated West Nile infection. They're the ones perpetuating this infection between birds and mosquitoes, or maybe infecting people or horses. And if you look at just that cohort, just those oldest groups, you see in your susceptible mosquitoes are nearly eliminated for up to 10 days. In your resistant mosquitoes, you still have a fair amount of them. 5 out of approximately 100 are still there. And you can see this wave pattern because those are the resistant gonotrophic, those are the gravid resistant mosquitoes perpetuating out further into the model, creating this kind of bouncing that is occurring. So, where old and susceptible mosquitoes are nearly eliminated, your resistant mosquitoes, they really persist and they remain a threat, and they allow that to continue on. So just in conclusion, we have widespread resistance to synergized pyrethroid products in our district, and then probably also across the state of Illinois. Mosquitoes after a blood meal develop a further resistance that really affects the age structure of the population. A reduction in treatment effectiveness is only one dimension of resistance, and that's the dimension that we usually come to understand, that we see some reduction in mortality. But there's a deeper kind of third dimension if you think about the age structure of a population, and that each cohort is different as an effect and is affected differently by ULV, and it's also differently affected by its risk of carrying West Nile virus. if you're only looking at total treatment effect, then the age structure doesn't matter. Total abundance is fine. You can just look at that. But if you're looking at a public health impact and what treatment is likely to really alter the trajectory of viral transmission, then the age structure of the population becomes a lot more important, and resistance really has a big impact, at least conceptually, just with a simple model on how that would look. So a modest reduction in control effectiveness may seem like it's not a huge deal, but it actually is a lot more serious because of the failure to strongly impact the age structure of a population. So I just wanted to highlight this kind of other dimension to resistance that I think is pretty important when we think about, oh, we have a 20% reduction in mortality. Does that really matter? Can't we just use more material, or can we just do it more often? Yeah, it does matter if you're looking at a public health intervention where you're trying to reduce the risk of illness in human populations. So with that, I just want to thank the Midwest Center of Excellence. They've been really supportive and helped us do a lot of this work through having interns or fellows or graduate students come and work with us. I want to thank some of our staff, Chris, who's our laboratory director, and then Roger Nashi, who helped design and analyze a lot of these experiments as we did them. And then Justin Harbison at Loyola, who also helped us conduct a lot of these experiments. And then Valent for being such a great collaborator with all of this. So thank you so much.